Raise your hand if you are seeing higher utility bills than you've ever seen before. Us too. Stick around. We're going to tell you what we did to cut our energy bills in half in 6 weeks.
Last January, my heating bill hit $400. I was furious. I tried everything. Nothing worked. Then I found a trick so simple it felt illegal. A retired physicist discovered it decades ago. The billion-dollar window industry buried it.
Larry and I, in July, received our utility bill. It was over $300, the highest bill we had ever seen as far as utilities are concerned. That's when we said, nope, this far and no farther. We are going to take this matter into our own hands, and we are going to figure out how to lower that energy cost. And that is exactly what this video is about.
I spent $4 at the hardware store, stuck something onto my windows, and went to bed. The next bill was cut in half. Just like that. No contractor, no permits, no expensive upgrades. The fix takes 20 minutes, and anyone can do it. They do not want you to know this exists, but now you will. To understand why that is, you need to know about something called an R value. It is a straightforward measurement that tells you how well a material resists the flow of heat. The higher the R value, the better the material holds heat in. The lower the number, the faster heat passes straight through it and disappears into the outside air. Every material in your home has one, from the bricks in your wall to the glass in your window frame, and the difference between them is not small. It is enormous. A standard wall in a home built to current energy codes in the United States has an R value of around 13. Some newer builds go higher, reaching R21 or beyond. That is a reasonable level of resistance. It means the wall is doing a decent job of keeping the warmth inside your home where it belongs. Now consider what sits inside that same wall. A single pane window has an R value of approximately 1, not 10, not 5. 1. Double pane glass, which is now standard in most homes and is widely marketed as an energy-efficient upgrade, gets you to somewhere between 2 and 3. Triple pane glass, the premium option that window salespeople tend to push as the top of the range, reaches somewhere between 3 and 5 under the best conditions. So your wall insulates at R13, and the window sitting inside it insulates at R13, and the window sitting. What that actually means in practice. Imagine cutting a large opening in your living room wall and covering it with a thin sheet of metal foil. That is not far off from what a single pane window does to the thermal performance of your home. The wall beside it is doing its job. The window is undermining it entirely. The United States Department of Energy has studied this in considerable detail. According to their findings, windows account for between 25 and 30% of all residential heating energy loss across the country. Read that again. A single component of your home, one that typically covers between 10 and 15% of your total wall surface area, is responsible for losing up to a third of all the heat your system produces. Your walls, your roof, your foundation, the floors, the doors, all of those combined. Account for the remaining 70% or so. Windows, occupying a fraction of the surface, are punching far above their weight in terms of energy loss. The reason comes down to basic physics. Glass conducts heat. It does not trap it. It does not slow it down in any meaningful way. It simply allows thermal energy to pass through it and dissipate into the colder air on the other side. When the temperature outside drops below the temperature inside your home, heat moves in one direction. It moves from where it is warmer to where it is colder. Through your glass, that process happens quickly and continuously. There is a partial offset during daylight hours. When sunlight comes through a window, it brings radiant energy into the room, and that incoming solar heat can partially balance out what the glass is losing. On a sunny winter afternoon, a south-facing window might actually contribute more heat than it loses during those specific hours. But that only applies while the sun is up. Once the sun goes down and the sky outside your window turns dark, that offset disappears entirely. Your windows stop receiving any incoming solar energy, and they continue losing heat outward at the same rate they were before. For most homes in the northern parts of the United States or across the United Kingdom and Northern Europe, that means somewhere between 8 and 12 hours of uninterrupted heat loss every single night, all winter long. During those overnight hours, your heating system is running to compensate. Every degree of warmth that passes through your glass and into the cold outside air gets replaced by your furnace or boiler, burning more fuel. you are paying to heat your home, and a substantial portion of that heat is walking straight out through the glass before morning. The financial cost of this adds up faster than most people realize. The average American home has somewhere between 8 and 10 windows. If you run those windows at R1 or R2, exposed to freezing overnight temperatures for 8 to 12 hours a night across a heating season that typically runs 4 to 5 months, the annual cost in wasted heat comes to somewhere in the range of $500 to $600 per household, according to estimates based on Department of Energy data. That is heat that was purchased, delivered through your ductwork or radiators, pushed into your living spaces, and then drained back out through the glass. You paid for it. It is gone. What makes this particularly frustrating is that the problem is not random or unpredictable. It follows a clear and consistent pattern. The weakest points in your home's ability to hold heat are known. They have been measured. The physics involved is not complicated or contested. Glass conducts heat poorly, and when the temperature differential between inside and outside is large, as it is on a cold winter night, the rate of heat loss through glass is significant and measurable. The window industry is fully aware of these numbers. They have been aware of them for a long time. The performance data on glass, the R values, the heat transfer rates, all of it has been studied and published extensively. And the industry's response to this information has been consistent for decades. They sell you a better window. Triple pane, low emissivity coatings, argon gas fill, improved frame materials. These are real improvements. Triple pane glass genuinely does perform better than single pane. But even the most advanced triple pane units available today top out at an R value of around 5 to 7, and they cost anywhere from $15,000 to $30,000 to install across a typical home. The payback period on that investment, the point at which the energy savings cover the cost of the upgrade, runs somewhere between 15 and 25 years by most independent estimates. That is a long time to wait on a product whose internal seals begin to degrade within 15 to 20 years, at which point the performance advantages start to erode. The argon gas that provides the insulating buffer between the panes slowly leaks out over time. The gap clouds with condensation. The frame materials expand and contract through seasonal temperature changes, and eventually you are back in the same position you started in. The fundamental issue is not which type of glass you have in your frames. The fundamental issue is that glass, regardless of how many panes it consists of, is a poor insulator compared to the walls surrounding it. And for 8 to 12 hours of every winter night, while your house is at its most vulnerable to heat loss, your windows are uncovered, unprotected, and losing heat into the dark. That is the problem. It has been documented, measured, and confirmed by independent research. And the solution, it turns out, is not a new window. If you told most homeowners that there was a fix for window heat loss that cost somewhere between $15 and $30 per window, required no contractor, no permit, and no specialist knowledge, and that it could match or outperform the thermal performance of the most expensive triple pane windows on the market, the natural reaction would be skepticism. It sounds like the kind of claim that falls apart the moment you look at it closely, but this particular claim does not fall apart. It holds up under scrutiny, and the reason most people have never heard of it has less to do with physics and a great deal to do with the economics of an industry worth $20 billion a year. The fix is called a thermal shutter. The concept is straightforward. You take a panel of rigid foam insulation board, the kind available at any hardware store for a few dollars per sheet, cut it to fit your window opening, and press it into place at night. In the morning, you remove it. That is the entire idea. No moving parts, no specialist installation, no ongoing maintenance. A piece of foam held against a window opening while the temperature outside drops and your heating system tries to keep up. The material most commonly used is either polyisocyanurate, usually referred to as polyiso, or expanded polystyrene, both of which are standard insulation products used widely in construction. A 1-inch thick panel of either material delivers an R value of around 5. Pressed into a single pane window opening with an R value of 1, the combination reaches R6, which already outperforms the best triple pane glass currently available. Increase the panel thickness to 2 inches and you reach R13, which matches the thermal performance of a standard insulated wall. The weakest point in your home's thermal envelope, the one responsible for 1/4 to 1/3 of your heating loss, can be brought up to wall-level performance for the cost of materials you can carry home in one trip. The man who measured all of this with scientific precision was William Shercliffe, a physicist who had spent the first part of his career working on the Manhattan Project during the Second World War. After the war, he continued in physics, eventually becoming associated with Harvard University, and by the late 1970s he had turned his attention to a problem that he felt was being systematically ignored by the building industry. He was watching an entire country lose enormous amounts of heat through the most obvious vulnerability in its residential buildings. And the only solution being offered was an expensive one that the same industry was profiting from. Shercliffe approached the problem the way he had approached everything else in his career. He measured things. He tested materials, documented performance figures, compared designs, and recorded results with the same rigor he had applied to nuclear physics decades earlier. What he found was not complicated. The physics of heat transfer through a window opening is not particularly difficult to model, and the solution he arrived at was, by his own account, almost embarrassingly simple. A rigid panel covering a window opening at night dramatically reduced heat loss. The numbers were not ambiguous. In 1980, he published his findings in a book he called Thermal Shutters and Shades. It documented over 100 different designs, ranging from simple foam panels to hinged wooden shutters with foam cores, sliding panels, roll-up shades, and accordion fold systems. Every design was tested. Every measurement was recorded. Every design could be built from materials available at a standard hardware store for under $30. The book was detailed and practical, and the data it contained was solid. No one challenged his numbers, no one published a rebuttal or disputed his methods. The information was accurate, the designs worked, and the book went out of print within a decade. By 2010, used copies were changing hands online for over $100 among the small number of energy researchers who still knew the book existed. Shercliffe died in 2006 at the age of 97. His book had been out of print for nearly 20 years by then. The window industry he had spent the later part of his career pushing back against had grown into a $20 billion annual market. But here is the part of the story that Shercliffe himself did not fully appreciate during his lifetime. He believed he was documenting a new solution. He was not. He was rediscovering a practice that had been standard across an entire continent for 5 centuries before he cut his first piece of foam. In Scandinavia, they were known historically as interior shutters, heavy wooden panels lined with insulating material, sheepskin, straw, or packed wool hinged to the inside of the window frame. Closing them at night was not optional. In a timber longhouse facing a winter where temperatures regularly dropped to -30 degrees Celsius, with no central heating and glass no thicker than a finger's width, the difference between a covered window and an uncovered one was not a matter of comfort. It was the difference between a room that held warmth overnight and one where the water in a bucket froze solid before morning. These shutters were survival equipment, in the same category as the hearth itself. The practice was not confined to Scandinavia. German buildings used folding interior shutters. English houses had their own versions. French architecture incorporated shutters as a standard element of window design. Every culture across Northern Europe had developed its own variation, different in materials and hardware, identical in principle. A panel across the window opening at night keeps the heat inside. The builders who used these systems were not working from R-value charts or thermal conductivity tables. They were working from lived experience in cold climates, and the feedback they received was immediate and unambiguous. A covered window in winter meant a warm room in the morning. An uncovered one did not. This practice continued in various forms across Northern Europe for centuries. It was continental in scale, routine in application, and universal enough that it required no formal documentation or instruction. Everyone did it because everyone who had experienced a winter without it understood the consequences. So why did it disappear? The answer is not a single event or a deliberate act of suppression. It is a sequence of developments that each made the shutter slightly less necessary or slightly less visible, until eventually it was gone from both practice and public awareness. The first major shift came with the widespread adoption of central heating in the late 19th and early 20th centuries. Before central heating, managing warmth inside a building required active effort. You banked fires, sealed drafts, and closed shutters at sundown because if you did not, the heat simply would not be there in the morning. Central heating changed the relationship between homeowners and heat loss almost overnight. If a furnace could replace whatever the windows gave away, the loss became invisible. The bill went up, but the room stayed warm, and the shutter went from being an essential piece of thermal management to being an unnecessary inconvenience. It did not stop working. People simply stopped noticing that they needed it. Then glass got cheaper and bigger. Through the 1920s and 1930s, improvements in manufacturing brought the price of plate glass down significantly, and architecture responded by making windows larger. Picture windows, bay windows, floor-to-ceiling glazing. Natural light became a design value, and large expanses of glass became a marker of modern living. Covering that glass at night with a foam panel contradicted everything the style was trying to communicate. The shutter shrank, then became decorative, then disappeared into those fixed plastic panels bolted to the exterior of suburban homes that cannot close, cannot insulate, and serve no thermal function whatsoever. They are, in a very literal sense, the remnant of something that once worked, stripped of every feature that made it useful. With shutters gone from the market and from common awareness, the window industry developed what became its dominant business model: the replacement cycle. The argument ran that if your windows were losing heat, the solution was better windows. Double-pane insulated glass units were marketed as the energy-efficient answer, followed by triple-pane, low emissivity coatings, and argon gas fills. These are genuine improvements over single-pane glass, but they come with two significant problems. The first is cost. Replacing all the windows in a typical home runs between $15,000 and $30,000, depending on size and specification. The second is longevity. The sealed gas units that provide the insulating performance of a double or triple pane window rely on seals that degrade over time. Argon gas leaks out within 15 to 20 years. Condensation begins to form between the panes. The frame materials expand and contract with seasonal temperature changes. The performance advantage the product was sold on gradually erodes, and the homeowner finds themselves back in the showroom. The regulatory system that might have interrupted this cycle instead reinforced it. When the United States Environmental Protection Agency launched the Energy Star certification program in 1992, it focused on manufactured products with model numbers, products that could be tested in a laboratory, certified against a standard, and sold at retail. It certified windows. It does not certify the act of placing an insulated panel against a window opening at night, because that act is not a product. There is no brand, no model number, no margin to be made on it. Building codes followed the same logic. The International Energy Conservation Code specifies glazing requirements, frame materials, and minimum window performance ratings. It has never, in any edition, mentioned thermal shutters or any form of movable nighttime insulation. Not because such solutions fail to perform, but because they exist outside the product economy that building standards are built around, the YOV. Result is a system where the $20 solution that outperforms the $15,000 upgrade receives zero support from the regulatory framework, zero presence in contractor training, and zero marketing budget. While the expensive alternative is certified, code-referenced, and sold through a supply chain that runs from manufacturer to distributor to contractor to homeowner with a margin at every step. Shercliffe saw most of this clearly. He understood the financial incentives. What he did not live to see was the moment when the most rigorous and scientifically demanding building standard on Earth validated everything he had measured and published, and built the thermal shutter into its core requirements as a matter of engineering necessity rather than preference. There is a building in Darmstadt, Germany that has been standing since 1991. It looks from the outside like a reasonably ordinary residential building. The people inside it go about their evenings in the usual way: cooking dinner, watching television, putting children to bed. What they do not do, and have not done for over 2 decades, is worry about their heating bill. Not because they are wealthy or indifferent to the cost, but because the building they live in was designed by someone who decided to take the physics of heat loss seriously and follow the numbers wherever they led, regardless of what the construction industry preferred to sell. That person was Wolfgang Feist, a physicist who founded the Passive House Institute in Darmstadt in 1996. Feist started from a question that sounds simple, but that the building industry had never wanted to answer honestly. What is the absolute minimum amount of energy a building needs to consume in order to remain comfortable throughout the year? Not comfortable under ideal conditions, not comfortable with the heating system running constantly, but genuinely comfortable across a full annual cycle of seasons, in a real climate, with real occupants, living normal lives inside it. The answer he arrived at after years of thermal modeling, field measurement, and iterative testing became the Passive House Standard. A certified passive house building uses no more than 15 kilowatt hours per square meter per year for heating. To put that number in context, the average American home consumes somewhere between 10 and 12 times that amount. A passive house building does not simply reduce your heating costs. It makes the concept of a significant heating bill nearly irrelevant. The building holds its warmth the way a well-made flask holds heat, not by running a powerful heating system, but by losing so little heat in the first place that a minimal system is all it needs. There are now more than 65,000 certified passive house buildings worldwide. They exist in Germany, Austria, Sweden, Canada, Japan, China, and in growing numbers across the United States. They include schools, hospitals, apartment blocks, single-family homes, and office buildings. They have been built in climates ranging from the mild and damp to the severely cold, and they perform consistently across all of them because they are built around physics rather than convention. The components of the Passive House Standard are well documented. Extreme levels of wall and roof insulation, often reaching R40 to R60, well beyond what any standard building code requires. Airtight construction that prevents uncontrolled heat loss through gaps and cracks. Mechanical ventilation with heat recovery, which allows fresh air into the building without losing the warmth already inside. And movable insulation over windows. Thermal shutters, external insulated roller shutters, internal insulated panels, automated systems with foam cores that close at sunset and open at dawn. The same principle that William Shercliffe documented in 1980. The same principle that Scandinavian and Northern European builders used for 5 centuries before anyone had a word for a value. Feist does not include thermal shutters in the Passive House Standard because of historical sentiment, or because he came across Shercliffe's book in a library. He includes them because the engineering demands it. Even the best triple-pane windows currently available, with low emissivity coatings, argon gas fills, and thermally broken frames, insulate at somewhere between R5 and R7. The walls surrounding them in a passive house building insulate at R40 to R60. The window remains the weakest point in the building envelope by a very wide margin, and the only way to close that gap without eliminating windows entirely is to add a removable layer of insulation that covers the glass during the hours when it is not contributing solar gain. During daylight hours, particularly in winter when solar angles are low and sunlight is worth capturing, the shutters are open and the glass is doing useful work. After sunset, the shutters close and the window performs at a level that approaches the surrounding wall. That is the logic. It is not complicated, and it is not optional in a building that is trying to meet the standard Feist set. The performance data on this is not theoretical. The Fraunhofer Institute for Building Physics in Stuttgart, one of the most respected building science research laboratories in the world, has measured the effect of insulated exterior shutters on window heat loss directly. On double-pane windows, the reduction in nighttime heat loss was 62%. On single-pane windows, the reduction exceeded 80%. Those are not marginal improvements. Eliminating 62 to 80% of your overnight window heat loss, the portion of your heating bill that disappears while you sleep, with a panel that costs less than a meal at a mid-range restaurant, is a result that belongs on the front page of every energy efficiency guide published in the last 30 years. It is not there because there is no product to sell. The contrast with how building codes are written becomes starker when you understand who writes them. The International Code Council sets its standards through committees made up of what it refers to as interested parties. The major window manufacturers, companies like Andersen, Pella, and Marvin, participate in this process through the American Architectural Manufacturers Association, whose members hold seats on the technical committees that determine which window performance requirements end up in the code. Every code cycle that raises glazing requirements without mentioning thermal shutters is a cycle that increases demand for the products those committee members manufacture. No conspiracy is required. Self-interest and a committee vote are sufficient. The result is a situation where the most scientifically rigorous building standard on Earth includes the thermal shutter as a core element of its thermal strategy, and the building code that governs the vast majority of American and British homes proceeds as though the YARM concept does not exist, which brings the question back to your house and what you can actually do about it. The materials required are available at any hardware store. A sheet of rigid foam insulation board, either polyiso or expanded polystyrene, 1 or 2 inches thick, costs a few dollars per sheet. You cut it to fit your window opening with a small margin on each side, roughly 1/4 of an inch, so that it fits snugly without forcing. If you want the panel to look presentable inside a living space rather than industrial, you wrap it in fabric. Cotton canvas works well, using spray adhesive to keep it in place. You apply self-adhesive magnetic tape strips around the edges of the panel and matching magnetic strips around your window casing. The panel then presses into place at sunset and pulls away in the morning. The magnet strips hold it firmly enough to create a decent seal against air movement around the edges, which matters because a gap between the panel and the frame allows warm air to circulate against the cold glass and lose heat by convection, even when the foam itself is in place. The cost per window runs between $15 and $30, depending on the size of the window and whether you add fabric covering. For a home with 10 windows, the total material cost sits somewhere between $150 and $300. The time required to cut and assemble all 10 panels is a single afternoon. The tools needed are a utility knife, a tape measure, a straight edge, and scissors. There is no contractor to schedule, no permit to apply for, and no installation that requires any skill beyond the ability to measure a rectangle and cut in a straight line. If you want something more permanent and better looking than a wrapped foam panel, Shercliffe's book documents hinged wooden shutters with foam cores that swing open like cabinet doors and when closed are indistinguishable from built-in cabinetry. Those run under $50 per window in mass. Materials and require basic woodworking rather than anything more specialized. They last indefinitely, they look like a deliberate design choice rather than an energy retrofit, and they perform at the same thermal level as the simpler foam version. The financial return on either approach is straightforward. On a household with an annual heating bill of around $2,000, covering 10 windows at night reduces the portion lost through glass by a substantial margin. Conservative estimates based on the Fraunhofer Institute's documented reduction figures put the annual saving at somewhere between $200 and $400, depending on your climate, your window type, and how consistently you use the panels. The panels pay for themselves within the first heating season, and often within the first month or two of use. The payback period on new triple-pane windows, by comparison, runs 15 to 25 years, on a product whose performance begins to degrade before that period is up. Shercliffe's book, Thermal Shutters and Shades, is back in print after spending nearly 2 decades effectively unavailable. The designs he documented, more than 100 of them, tested and measured with the precision of a physicist who had spent his career taking measurements seriously, are accessible again. The information was never wrong. It was simply inconvenient for an industry that had built its revenue model around the assumption that the answer to window heat loss had to be expensive. The physics has not changed. Glass conducts heat. Nights are long in winter. A foam panel costs $20. 65,000 buildings across 30 countries have demonstrated what happens when you take that combination seriously rather than ignoring it in favor of a more profitable alternative. The solution is not new, it is not complicated, and it is not waiting on any further development or certification. It is sitting on a shelf at your local hardware store, waiting for you to cut it to size.